terms of the development and the upcoming solution in regards to the universal settlement network. So what is settlement? Settlement is the ability of finalizing a transaction where the transaction is not able to be reversed. Over here we have a list of the various different types of confirmations required for a Kraken withdrawal to be accepted. So Kraken is an exchange, it's a centralized exchange. In order for them to process your withdrawal, you need to essentially wait a few block confirmations. In terms of, we recently had a fork for Ethereum proof of work, and in terms of Kraken, the finalization period is 20,000 confirmations, so which takes roughly 3 to 4 days. Versus Ethereum, and the Ethereum network takes 14 minutes for finalization to occur in the proof of stake network. So this is due to the design of the overall mechanism of finalization. With epochs and all that. We also see Ethereum Classic needs a lot more confirmations. Not as much as Ethereum Proof of Work, but 2,880, which takes roughly 12 hours. The reason for this is because some blockchains have the ability to essentially be under a 51% attack. And as a result, exchanges don't want to process transactions, in which case they give you money, but the transaction in which you gave the money reverts. So this is a very common problem across every single blockchain. It's the issue of settlement. Where does settlement happen? And this is a main issue in the sense of cross-chain interactions. How can you guarantee that a certain transaction has occurred without it reverting at a later time? So universal settlement is where any computation can be executed by one blockchain, and the results of the execution can be resolved to any other blockchain. Oh, so a lot of movement there. So we've coined the term entangled rollup in ZKM. Essentially, it's a way to trustlessly pass messages using from one chain to another using zero-knowledge proofs, as well as roll-up design, layer 2. Wow. Okay. This clicker is a little bit janky. This is a complicated diagram, hopefully a little bit simple, but we get to see that messages essentially start out from the layer 2 node and then finalize to a different layer 2. But the transactions all settle on the layer 1. You would essentially generate a proof that the transactions are finalized on the layer 1. And then from that finalization, you can then post that to a layer 2. So this mechanism means that because you are interacting with the layer 2, which eventually resolves to a layer 1, you can benefit from the gas cost reduction and essentially still utilize the same level of security as that layer 1 without introducing a additional consensus mechanism as very common in many different types of bridge-based solutions. So what does that complicated diagram simplify down to? Well, we essentially can connect various different types of networks together that are not related by VM, but the ability to talk to each and every single network using a network of connected layer 2s. So, which all get settled on layer 1, but as a result you are able to guarantee that the transactions are finalized without incurring an additional security assumptions. Oh, can you click on the slide? I think yeah, there we go. Okay, so this is what we coined the Universal Settlement Network. we have a universal L2, essentially native verification with shared liquidity. The mechanism behind this is if I deposit 100 USDT on one layer 2 and 100 USDT on a different layer 2 on a different ecosystem, they're all interconnected via this network of layer 2s. Essentially, every single deposit that occurs, you can share that liquidity across all those connected layer 2s. So how does this structure work? As a simplified diagram, we have layer 1 Ethereum where we can deposit 100 USDT to the universal L2. And that's essentially connected with each other, where we can now burn a specific amount of USDT. We can then wait for that transaction to finalize on layer 1. After finalization occurs, we can, based on the likely the amount of block numbers as Kraken had done it, we can then generate a ZK proof, essentially proving that this transaction had occurred and that that USDT was removed from circulation. So using this proof of burn, we can then go to another layer 2. And the way that layer 2s work is that when you deposit USDT, let's say from an L1 to an L2, that uses the native mint function on that L2. So what that means is that now I have an alternative native mint function, which accepts a valid ZK proof. Therefore, I don't need a counterparty. I don't need a liquidity provider. I can use the native mint function of this layer 2 by providing a valid proof of burn. And that way, I can share assets across different L2s, proving that I'm not minting any more than I burn. So there's a number of pros here. One is that this is trustless by design. I am trusting the ZK proof that is generated. The finalization parameters are all public. Everything is essentially generated through the lens of I have a proof of burn, and I take this proof of burn, and I can send this off to any layer 2 connected within this system. This is also interoperable. It can work with both EVM and non-EVM chains. As ZK MIPS, we are proving computation in a ZK VM, which essentially means that we can prove any form of computation on any program that compiles down to bytecode. The other point, and I think this is what a lot of projects are focused on, is liquidity optimization, where we essentially take the deposits that are run by the different layer 1s, and we can share this across the different interconnected layer 2s. And because these layer 2s don't have to be on the same layer 1, we can essentially take this and grow it to whatever networks. So it could be, we've seen recently that app chains are very popular. App chains specifically on Ethereum. But then we've seen that, for example, Movement is deploying a layer 2 on Ethereum where they're adding the Move VM into that layer 2. And the thought process is more layer 2s are likely going to be deployed on networks that likely are not supporting either EVM or non-EVM. So just like how Movement's deployed on or is deploying their layer 2 on Ethereum to support the Move-based language, we're seeing layer 2s deployed on Solana that are supporting EVM. We're seeing these different layer 2s that are providing, like Aurora, that is deployed on Near, that also support EVM-based computation. So essentially, we can take different types of networks, and even though they don't have a shared L1, we can still share the liquidity across different networks, incompatible networks. And then finally, L2 scalability benefits. which is essentially liquidity retention. You have an L2, and then this essentially provides value in terms of reducing the transaction fees and increasing the transaction speeds. So an extension also, actually there's a few cons that needs to be mentioned. So I mentioned that there was the native mint function that is required in order to process this. So likely more established layer 2s are potentially not entirely willing to give away their native mint function to essentially like a project that comes in and says, oh, we'll share money across everything. So essentially what this needs to be done is built into the rollup on when the rollup is created. And so we're seeing a lot of services, rollup as a service providers, essentially come in with pre-built modules that already come with this let's say, mechanism of cross-chain interactions. But then utilizing the ability to prove any computation across any virtual machine, this can be used as, even though this adds potentially risk that if something bad happens, I can mint any amount of tokens on that layer 2. But assuming that everything's audited, everything's secure, we can see much more use cases derived from this because it's more maneuverable as a result. Also, dry spots. So if I deposit from layer 1 to layer 2, and let's say on the Avalanche layer 1 to layer 2, I don't have any liquidity, I cannot withdraw on Avalanche. But in this case, I can essentially, I don't lose the money. I can essentially generate another proof of burn on the Avalanche layer 2. So instead of withdrawing to layer 1, I can generate another proof of burn and then withdraw to where there is liquidity. So in this case, on Ethereum. An extension to this, so very interesting EIP that I read a while ago, 7503, zero knowledge wormholes. Essentially, you can generate a public looking address, an address where you can attest that nobody knows the private key to this address. So essentially, you generate a zero knowledge proof that this public address, that it isn't a like 0x000 or 0x dead, like the typical burn address. It looks like a real like 0x ABC 123. So you can generate a proof saying that nobody knows the private key to this address, and as a result, since nobody knows the private key to this address, when you send funds to it, it's essentially burned. So the same mechanism still applies, where we can essentially generate a proof of burn to what looks like a public address. And nobody knows that you've actually burned the funds. People see that you transferred it, but nobody knows that you're actually using this type of proof of burn system. So this can generate interesting use cases where I am publicly sending money to here, but then I'm generating a proof, which then allows me to mint on a different destination L2. So this is the same process, but in this case it's private. We don't know where you're going to burn the assets, and then when it's redeemed to the destination L2. So when it's redeemed, people will know that you burned assets at some point, but it's not revealed up until that moment that you redeem. So it could be useful for different types of when you for privacy-based purposes as well. So the settlement network at its core implements validity proofs as a means to transfer assets. And validity proofs are verified in the destination chain, and the specific portion of this is that no intermediary blockchain is required. So why we're creating this complex architecture? Specifically because we don't want to rely on a less secure chain in order to guarantee that the result is settled. So I do have like a very, very quick demo. It's not too intensive, but essentially the steps for this is to generate a proof of burn from a block state transaction, from a state transition on mainnet, and then we submit a proof of burn to another blockchain. So this just goes through the process, taking the block, running it through minigeth. It goes through, it correctly processes with the hash. We can then generate a proof from this, and then if it doesn't skip, we can take this proof, submit it to a contract, and then as a result, this would mint ETH. Okay, well, you'll see in a moment. It's essentially this website, playground.zcam.io, and we can just like really quickly just refresh that. But essentially, we can just generate a proof using a burn transaction from the 0x dead address. We can take the value of ether that burn transaction has occurred. We can generate a proof off of that, and then we can receive it on a different address. So I think it's still loading, but we'll see if it's still refreshing. But anyways, the demo is live. You do need Sepolia ETH, so that's like the downside, but you can try it out. It's playground.zcam.io. Essentially, you just log in with either your MetaMask or a Ravi wallet. You just click generate proof. After it generates the proof, you wait 100-ish seconds, and then you're able to mint those tokens. And I think I have the end result here somewhere. Just to give you a little bit of a flavor to this, we have a couple of, well, not on mainnet, on Sepolia Etherscan, and then over here, you can then, yeah. So essentially over here, I have minted a corresponding amount of tokens from a burn address with the correct proof inclusion. So that's the entire life cycle of the process, and yeah, essentially that's the workshop.
Thank you.